Okay, sir, tell us about good, bad, and unacceptable roofs.
And the ugly, actually. So, has anybody been in a commercial building and seen insulation on top of suspended roof or suspended ceiling? Yeah, that is absolutely not acceptable. It is a terrible, terrible design. It does not work, and the code bans it. I mean, you've got multiple issues there. We talked about having a continuous air barrier. Maybe the insulation's sort of in contact with that, but you've got, you've got a 2x2 tile up there. You've got 8 linear feet of crack right there. People are getting up in there. They're pushing it around. It's not a very good system, and the code recognizes this and said you absolutely cannot do it.
It's been banned. Yeah, it's not continuous either because you have light fixtures and stuff in the way. It's been banned in the code since 1999. Yes?
Could sound that for like that?
You can absolutely
put that for sound. So
our recommendation, though, is to not use fiberglass unless it's an encapsulated bat or to use another product like they make. I don't know if I have a sample of the cotton. There's a cotton bat. One was made in South Carolina. There's also some neat products, like this is a cellulose bat that has really good acoustic absorption. I think it would be, a product like this is less likely to become an air quality issue down the road. You know what happens to fiberglass bats over time is they start to become friable and they start to basically release fibers into the air, and it's not really good for you. Here, catch the steel stud. Here. The cellulose, what is the raw material for cellulose insulation? Does anybody know? Yeah, old newspapers. So it's almost 100% recycled content, and it has a small amount of borate as a fire retardant. And borate has some nice benefits. First of all, for humans, it has about the same toxicity for us as table salt. In other words, you can eat it, and you should live. Don't eat it, but we have lunch provided. But the other thing is that borate. What do you think about bugs in borate? Anybody know that bugs hate borate? It's a very natural, or it's a very good means. It's very benign to humans, but very good means of deterring bugs. So there are some benefits of it, and we even have some. There's a company, for example, in Gainesville, Georgia, that makes a borate-treated foam board, where the borate is in the foam, and that would be in the ICF system that we used for our building. There's borate in the foam, so if a bug, there's no wood in there, but if a bug tries to tunnel through it, it'll die. So that's kind of a nice feeling. It makes me happy to think that a termite would die. Anything taking down the termites. Does that kind of make sense? So I think there are some other options for that. You can do it for acoustics, but you absolutely can't do this for a new construction and to count it as your insulation barrier.
Oh.
Questions on that?
And if you touch it, actually, so this goes back to, we were having this discussion in our last class that we did up in Norcross, Georgia. A lot of people go in and they'll retrofit. If you get into that ceiling and you take that down, you're going to have to put something in, either on top or below. You're either going to have an R38 somewhere in there, or you're going to have an R20 continuous insulation on top of that roof.
We'll talk about how you can do that, but that is true. When you go to an existing building and you renovate it, well, first of all, we're going to have a lot of work ahead of us. We, as an industry, have to fix a whole lot of buildings that did this. We have to fix those buildings because they're wrong and they don't work and they're a really bad idea. But we built a lot of them, right? And we, unfortunately, continued to build them long after they were illegal. So, and perhaps some people still build them today. So we're going to have to fix a lot of these, and that's sad. And we'll talk about how we think there's a couple ways we can fix it, but let's move on. I mean, this is one option too, is that we could put the insulation instead of being, on the drop ceiling. The code does allow us to put the insulation, let's say, and create almost like an attic, and we have to put a hard air barrier underneath it. And how much R value do we need in this example? 38. Very good, 38. So in that situation, it can work. What are some maybe issues with this? Yep. The trusses, or the ceiling joists have metal, and that's highly conductive, and that's going to affect the performance of the
Which is
assembly.
why you've got an R38 as opposed to an R20. You're also going to have to make sure that if your insulation previously, if you had this condition before and you're going to this, that insulation has to run off the wall. Again, we've got to have that continuous envelope, a continuous building envelope.
And I think, one advantage is changing the design here is that, of course, now we do have our ductwork inside the envelope, which is very good, but we still have the issues of, because this ceiling is hidden by this ceiling, this is where ugliness will occur. When I say ugliness, meaning somebody will not really do the best job because no one's going to see it. Or this wall right here will not really be air sealed very well. Or this ceiling, someone will poke a hole through it to run a wire. No one's going to see it. I don't have to, why should I seal it back up? So that's one of the things I think that we really find is, drop ceilings hide the ugly stuff in commercial buildings and the holes. That's where they are. So we anytime we do an energy assessment, that's where we immediately start looking, is push the tiles along and see where the ugly stuff is, because that's where it is. Okay. A retrofit option that I think can work very well is spray foam underneath the roof deck. Has anybody done this on a commercial building? What was your project? Uh-huh. Sprayed it on the bottom of the roof deck, and then did you, yeah, I was going to say, did you leave a suspended ceiling or just take that whole thing out? Yeah. I like that a lot.
Did you see significant energy savings? Yeah.
Unfortunately, the guy who sprayed it got too much in the first couple of days, so he couldn't change it. So he's used obvious material in the first third, so he had to keep pumping it to make it look uniform.
Sounds
So you got
like
a bonus.
they lucked out there, yeah. Wow.
Well, let me tell you that I think this can work really well. This is it's a little hard to see, but these are some photos. My kids go to preschool in Atlanta, and they had an old building, and this is a great statistic. They had an old building that was, I don't remember how big, probably in the neighborhood of 3,000 square feet, something like that. But it had old, inefficient, the older fluorescent lighting in it. And it had, basically, I don't remember if it had insulation on the drop ceiling or not. But we went and did a renovation on it, and we sprayed foam on the roof line, and we sprayed an R19, which is about 6 inches of open cell foam. We sprayed, the wall only went up to here, so the other walls also had to be insulated, obviously, as well. And then, so it was really just insulating the roof and replacing the light fixtures. And we knocked the cooling capacity from 12 tons to 8 tons. So just that one, those two changes, basically cut a third of the load down. And that was, I think, a pretty dramatic statement. The one thing I want to say about foams is, everybody understand that there's two kinds of spray foams, right? There's open cell and closed cell. I think we have a sample of each one. I don't know if we have the open cell. So what kind did y'all use? Do you remember? Yep. In a commercial application, you're probably going to have to do that. Did you use the open cell or closed cell? Okay, that's all right. Probably the closed. So the open cell foam, whee, what's it mostly made of? Air. There you go. The open cell foam is about the same R value per inch as fiberglass or cellulose in a cavity. So in other words, you spray this in a 2x4, you're going to get R13. Everybody get that? Spray it in a 2x6, you're going to get about an R20. Okay? It's very lightweight. I could literally just easily poke my finger through my sample here, right? So this is the open cell foam. It's sometimes called half-pound foam or low-density foam. And it is this roughly R3.5, 3.6 per inch, is a typical value here. To get an R19, which is what we typically are wanting to see, it's a 6-inch application. So you're looking for about 6 inches of sprayed foam. That's for open cell. Okay? The closed cell foam is very different. I'm going to hurt my hand here. Closed cell foam is sometimes called 2-pound foam or 3-pound foam. It's a higher density foam. And the closed cell foam is almost double the R value per inch. So I'm just going to use it approximately 7 per inch. So to get an R20, you're looking at 3 inches. Okay? And the key thing in any insulation, but particularly with the closed cell foam, is consistent application. And that's what Dave was saying, is that you got to spray the right amount and you got to keep it consistent because, well, I'll say it's more critical with the closed cell than the open. The open cell, you shortchange me an inch, okay, I'm going to lose an R3. But you shortchange me an inch on this, I'm going to lose 1/3 of my R value. So the consistency is the big, big number here. Let me see if I can find I should just open another folder.
I think, give us your views on this, Mike. Again, if we spray on the underside, we're supposed to have an R38.
Yeah, this is what I wanted to show is this picture right here. I don't know if you can see that, hopefully. But this is where they've sprayed the closed cell foam up against the roof deck. And the consistency of this, getting a consistent 3 inches, is the key thing. And so code officials, this is something where you really do want to kind of give them a hard time about it. I hate to say it, but that material is expensive. So the subcontractor a lot of times might sort of err on their own favor. So, but it's consistency that makes this stuff work. The other thing is you got to be aware of BS in this industry, where people come in and they say, 1 inch of my magic foam acts like R50. Have you ever heard that? And generally, I mean, that's absolutely not true. That is not true. And they'll say, well, because it also air seals, it performs like an R30 or something. It's like, no.
They'll start talking about effective R values.
Yeah, that's not true.
You have to be careful. It's the real R value. So you've got to have, again, in that application, you've got to have an R38. We could argue whether or not that's really, there's probably some truth to the effective R value, but in closed cell foam, that means 6.5 inches.
Yeah, so the answer is really for spray foam against the roof deck, you're not meeting the code. It's a very good system, but you're going to need to do a trade-off because you're not meeting the prescriptive R38. The R20 continuous insulation is where it's above the roof, but this is below, and there is framing in the way. So it's not going to meet the prescriptive code. Unless you can get, like Brandon said, R38. It's not worth it to go R38 on foam. Foam, you hit about R20, and that's the point where economically it's kind of hard to justify going more. Does everybody get that? That's an important statement.
Are you saying in this application, though, code-wise, you've got to be an R38?
Well, if you follow the prescriptive path, right. And this is sort of where we're going to get into a com check, is we think this is a great system. But you can probably, because of the expense of it, when you start getting too thick, it gets really expensive. So let's do some trade-offs.
Yeah, it
and
doesn't.
That's possible.
The code does not have a separate application for sprayed foam.
Yeah.
It just says insulation that's not continuous above the roof deck has to be R38. And spraying R38 would be very cost prohibitive and not really beneficial. After about R20, you really are hitting the point of diminishing returns.
Most roofs you're going to have some type of insulation on the deck anyway.
Certainly. Again, remember we've got that U factor, so you're going to talk about that. Look at that assembly, which will look at air films. It'll look at your roof membrane. It'll look at your decking. It'll look at your continuous insulation on top, and then take that into account.
And again, the beautiful thing is that ComCheck, you can design this into ComCheck. It'll figure it out for you. So.
The bad thing when you have roofing is when you re-roof and take the insulation off, it's a throwaway product.
Yep.
So you hate to see all that valuable stuff going to land.
Yep.
So, that's a problem there.
I agree. I mean, if there's a way to salvage it, if it can be saved. I've seen some commercial roofs that use a closed cell spray on as well. Have y'all seen these before as well? Or lightweight concrete. There are options out there, but at the end of the day, from a thermal standpoint, the best place for insulation is outboard of the structure, and that's what we're doing in this case. And the insulation up on the roof deck, I think, performs very, very well. And if you think about it, it's continuous. It doesn't have interruptions in it. It doesn't have thermal bridging through it. It works, and that's probably the best thing you can do in terms of insulation. But if you rip it off, yeah, you have to actually bring it back to code. And that, typically the roof insulation you see is this material. It's the polyisocyanurate, right? That's the most common commercial roofing material. That stuff does not do well from the sun, so you don't want to leave it exposed to UV. But this stuff can get you to the R20 with 2.8 inches is what it says. So, and yes, it has to be the minimum thickness. It's not, you can't prescriptively again, you can't say, well, I started off at R20 and then I tapered it down to R10. That doesn't work. You could do a trade-off, but that's not going to meet the prescriptive code. So everybody good with this? Everybody see where we're kind of trying to push you on roofs? There's another thing that's kind of neat that's recognized only in ASHRAE, not in the Chapter 5, and that is that shiny roofs get credit because they absorb less. And Brandon, you want to kind of take us through this one? That's an example of a very reflective roof right here that's connecting our old building with our new building.
So again, back to sort of our building science principles, these white roofs are not going to absorb as much radiation, and that's a major heat source. And so they're saying, hey, we'll give you credit for this. So instead, we're talking about R20 continuous. We can actually drop that down to an R13. Another thing we like to talk about is the heat island effect. We've actually got some thermal imaging data. This is Atlanta, actually, in 1972. You can sort of see downtown. This is the beginning of what? Does anybody know what this is?
What's that little lower red splotch just near the perimeter right here?
It's the airport. Exactly. 93, move ahead another 11 years. Wow, we've had a lot of growth. The airport's grown. We've got another big one up here. Does anybody know what that is? Gwinnett County. Yeah, I heard Gwinnett back there. Fastest growing county in the nation. So they put a lot of, they didn't build up, they built out. A lot of streets, a lot of infrastructure, and you can actually, it's physically reflected on how much heat that is gained. You look at those red spots; they're probably about 10 degrees cooler, 10 degrees warmer than the surrounding areas.
So this is a very real effect, the heat island effect. Joe, you're a mechanical guy, right? It affects your equipment because you're designing equipment to reject heat, and the air is supposed to be 95 degrees, but it's significantly hotter now because the local ambient, in essence, is so much warmer. It kind of comes down to, in my simple version is, what would you rather walk barefoot on a hot day, concrete or asphalt? I think we know the answer to that one, right? So what would you rather put your tongue on? It always comes down to that. So it's an interesting phenomenon. What's funny is, this is what we measured for Atlanta last year. We got this. This is our climate zone map. I don't know if you can see that, but that would be the point where you could laugh right there. You can hot Atlanta. That's it. All right. No one laughed at that, so we're moving on to the shiny roof credit. That's what I call it. The shiny roof credit. This is only in ASHRAE, but what ASHRAE says is that if you're in climate zone 3 and you were required to have R20 at the roof, with a shiny roof, you can only have R13.
Or, instead of R38, you've got that R25. We were talking a little bit about what were the requirements for solar reflectance or solar reflectance index. There is no code requirement, but if you want to take this credit, you can either take a look at the manufacturer specs, and it says if it's got a minimum solar reflectance of 0.7 and a thermal emittance of 0.75, or they have this thing called an SRI, the Solar Reflectance Index. They have an SRI of 82. If it meets any of those criteria, you can take these credits. So check with your manufacturer.
There's a problem with that, though. I was at a motel a couple of weeks ago where I was looking down on what was probably a TPO, white TPO.
Dirty.
Right. Get dirty.
It
Yeah.
was as brown as this.
Yeah.
Really?
Oh, it was.
Usually it gets kind of gray.
You've got to be losing both.
Yeah.
You're losing. These are actually aged values, so they're trying to take that into effect. But it's a very true statement, I think, from an operations standpoint. You want to make sure that you're cleaning these things ever so often. Unfortunately, the code does not mandate cleaning.
Yeah, sadly. It still works better, but that's pretty brown. The other thing is that Georgia decided that we would give the same credit if you put a vegetated roof on a building. Has anybody done a green roof on a building, a vegetated roof? That's an option that's obviously more expensive, but we're going to basically say, look, it's going to have the similar performance as if it's a shiny roof membrane. So we added that. That's the only provision we actually adjusted the commercial code on in terms of ASHRAE. And I'll tell you a little story. I don't know how well it's going to show up on this, but we have some friends that are doing some research over at Georgia Tech Research Institute, GTRI, and they're looking at different roof surfaces and the impact on photovoltaics. Because you may not know this, but PV panels, obviously they convert light into electricity. Well, they operate better if you keep the panel cool. And the temperature of the roof, is a factor of, how that panel is going to perform. So they're looking at different roof surfaces. And they're in a big old building that has a light ballasted roof, and we went up on it, and it was a 90-degree day, and it was hot. We go up on the roof at noon, and walking around up there, and I mean, your face is just cooking. It is really hot. You walk around, and the light ballasted roof. There was a less than 2-foot square sample of vegetated roof. A little roof tray, if you will. And we're looking at this. It had been up there, and we looked at, with a thermal camera, the temperature of the ballasted roof was 150 plus degrees, and the temperature of the vegetated roof was, less than 110. And so it was amazing how much cooler it was with the vegetated roof. It was remarkable how much cooler it was. And I thought that was a very compelling evidence. So this stuff works. It really does work. Oh, 3 inches maybe, something like that. And there's a lot to vegetated roofs. But this leads us to this other thing that we really like, that we want to, tell us a little bit more about vegetated roofs, Brandon, I guess.
Well, sure. I mean, that leads in well. There's a couple of different types of vegetated roofs when you're talking about. There's extensive and intensive. So an extensive is usually a fairly shallow, 3-4 inches. They use sort of an engineered soil medium. It's sort of almost like a lightweight ballast. Typically, what you're growing in these are plants that don't require as much water. They're succulents. Or you can have something called an intensive. You've got people that have done these things about 3 feet deep, and they'll hold full trees. It just depends on the application.
In the budget.
And the budget. And extensive, you usually don't have to beef up structures much, so it can be a lot more cost effective. My personal opinion on green roofs is they're great if you can use them as an amenity. If you've got people who can actually see them. It's probably not the smartest use of your budgetary money if nobody's going to see it. Put a white roof up there.
Yeah, I agree with that.
But it can work well as a system.
This is the system that we actually have. That's the City of Atlanta building, but we have a vegetated roof, and our system uses this assembly where it's a deck, a concrete deck that has the waterproofing membrane. And then on outboard of that is the insulation board. And then you've got this kind of assembly where it's a kind of a filter fabric and a series of these plastic cups that can essentially absorb some of that moisture when it rains, and then the engineered soil, filter fabric and engineered soil. And the plants can grow and the roots can grow down into these, and that's why they can survive. And you plant native plants that are adaptive, or sedums and things, and they can handle that environment. And our vegetated roof, it looks really good. When probably in a couple weeks, it'll be fully bloomed out, and it looks really good. It's a nice look. And like Brandon said, it's an amenity. It's a rooftop garden. So when real estate's at a premium, I think it makes sense, but it is expensive. This approach, though, is kind of interesting. The roof membrane is here, and the insulation is on top of it. And so we really like that concept, and we call that an IRMA, inverted roof membrane assembly. Inverted roof membrane assembly.
Does anybody use that on one of their buildings?
Let me talk about well, there's really two things that cause a roof membrane to fail. There's two things that cause a roof membrane to fail. One is what? What do you think was the most obvious? What cooks a roof membrane? The UV from the sun, right? So that's obviously a big factor. The other thing that cooks a roof membrane is thermally cycling it, meaning heating it up and cooling it down, because that's going to cause it to expand and contract, right? So over the course of a season and years, we're heating it and cooling it. We're causing that expansion to occur. So if you can essentially deal with both of those issues, you're going to find that the roof membrane lasts a lot longer. And a lot of this research they've been doing this in Europe, where they do a lot more vegetated roofs in Europe. And then what they're finding is they're doubling the life of the roof membrane. So a 20-year membrane becomes a 40-year membrane. And you can do this, like we showed in this picture, with a vegetated roof, or the one that we have on our atrium. It's essentially, there's the roof membrane goes down, and then we have some thickness of insulation, and then we have these panels that are tongue and groove that are 2.5 inches thick, 2 inches of foam and a 1/2 inch of concrete on the top. They interlock, and the concrete is painted with a shiny reflective coating. And so you get, that was that picture we saw a couple slides back, that one right there. This is what it looks like from the air, but the effective, the way it works, I meant past it, is that you get some sheet flow off the top, but the real drainage surface is down here on the membrane. Does that make sense?
And I think I've even seen it done with like just a ballasted, just using ballast on top of the insulation. It's not going to give you the reflective value as much, but no, it can work. It can work.
But the bottom line is that this is an assembly. I think that it's if you want to look at the life cycle effect of the roof, if you can double the life of the roof membrane, there's some value, big time, added to that. So you look excited by all this. So I'm sorry, I'll push forward. Does anyone have any thoughts on this? I would encourage you to look at roof assemblies where you might be able to apply the concept of the IRMA, which is the membrane goes first, the insulation is outboard. Obviously, we have to protect the insulation with something, a vegetated roof, a ballasted roof, or I like these panels. I think that's a neat concept. Okay, we're going to wrap up the tables by looking at the glass. The prescriptive code on the fenestration, once again, you have to be less than 40% windows and 5% skylights. So how do you do that calculation, Brandon?
So we've got a building here in this example. It is 100 by 150 feet and 20-foot high walls. How big is our wall area? So we take 100 plus 150, that's 250, double that, that's 500. We've got perimeters 500 feet. Is that a fair statement? Times 20, what's that give us?
500 times 20, it's 5,000.
10,000. So we've got 10,000 square feet of surface area. And then 2,000 square feet of windows and glass doors. So what's our percentage? 20%. So can we follow the prescriptive path with this particular building? Yes. Yes. It's under that 40%. We're at 20%. Absolutely.
Okay. So as long as you don't exceed 40%, then you're good to go. And the basic thing here is the code would like us to have this information, the U factor, the solar heat gain, and the air leakage information. Visible light transmittance is sort of what we want. Why do we have a window in the first place? It's to let light in, right? So we want that. The ideal window has a high visible light transmittance, but it has a low U factor, a low solar heat gain, and a low air leakage. Because basically, if you think about it, we're dealing with conduction, we're dealing with radiation, we're dealing with convection, and we're dealing with light transfer. Okay? Any questions on that?
So go back to the previous slide, though.
This is a challenge.
Is this information easy to get on a commercial building? It depends. If you've got a window that you've bought, it's a full unit, yeah, it's going to have a sticker on there. But what happens with a lot of buildings? We have field built. You know, we've got storefronts. So we've got a storefront system. We put glazing in there. They don't come with these stickers.
Uh-oh.
So, but there is, if you're a code official, you can ask for this. If you're a designer, you can ask for this information. The storefront manufacturers actually have tested their storefront with a wide variety of glasses, of glazing options, and they can figure out what your U factor is going to be and what your solar heat gain coefficient will be. The building I was talking about, we'd renovated earlier this year, our Suite Center, Southeastern Weatherization Energy Efficiency Training Center. We had YKK donate the storefront product, and then Viricon donated the glass. And they actually had, it's a sheet that they come, and it has all the information. If you put this type of glazing in there with this particular U factor or this particular solar heat gain coefficient, it's going to give you the entire assembly. They have to sign off on that. The glass manufacturer has to sign off on that, and the contractor has to sign off on that. You can get this information. Code officials can ask for it. That's one. It's sort of difficult and it's different because I don't think a lot of people are asking for it, but the information is out there.
Okay. So basically, if the R value and the U factor, we talked about how those are related. You know, single pane windows are about an R1, double pane windows are about an R2, triple pane windows are about an R3. You don't see that many triple pane windows, but they can get the performance of a triple pane by using low E coating on a double pane glass. So we can get a window that looks very clear, but it's actually going to perform very, very well as if it were a triple pane. And it's cheaper to do that. So the other thing is that low E helps us, I will just say from the commercial code standpoint, it's pretty easy to hit the U factor requirement that we need. Where it gets challenging is hitting the solar heat gain coefficient. This is in many ways kind of the tail wagging the dog in terms of your glazing selection. And that has to do with solar gain. Because if you think about it, what's more important in a commercial building in Augusta, Georgia? Air conditioning or heating? It's cooling it, right? Keeping it cool is the more energy is going to be spent on that. So keeping the solar gain down, a single pane glass, 80% of the sun's energy passes through. A double pane glass, 60% shines through. A double pane low E, we can get down into the 20-25% of the sun's energy passes through. So it's really important that we select glazing carefully. And I will say that the code keeps pushing this number way down. And it's a very big deal. So the chart, once again, the requirements, the chart looks like this. This is the lower half of the entire table. You've got the entire table in the back of your book. And basically, the U factors, depending on the type of frame, are all in the neighborhood of 0.6-ish, or an entrance door is 0.9.
We were just looking at that previous page. What's the U factor of a one-pane window? It's 0.55. That's going to get you there.
Yep.
Easily. And for the most part, we're going to be putting in double pane. It's this solar heat gain coefficient of 0.25 that's going to be much more difficult to get to. That's the driving factor on windows here in Georgia.
Okay, so climate zone 3, it's very much about reducing the solar gain through the glass. And I think you need to remember 0.25 is the answer. That's what you have to hit. Now, you can hit that with just the glass. It can be done. It's not the easiest thing, but our Suite Center did that, right?
I mean, so we're an environmental organization, YKK, Viricon, they wanted to showcase some of their high-performance glazing, some of their thermally broken storefronts. was saying, there are some options.
So one of the biggest things is you are allowed to take credit for overhangs that shade your glass. And this will help you a lot, okay? So whatever your glass actual solar heat gain is, if you've got a certain size overhang, it's this term projection factor, you might get to multiply your glass by 0.82, for example. So the size of the overhang and the distance between the overhang to the bottom of the glass is a factor that's coming into this thing called projection factor. All right? Don't overthink projection factor. It's literally how big is the overhang and how far is it from the bottom of the overhang to the bottom of the glass. So it's A over B. If A is 4 feet and B is, I was going to try to pick a good one, 9 feet, what would that be? Ooh, that's hard. That'd be like what? 0.45 or something like that? 0.45 U factor? Or projection factor. It'd be what? 4.4. So that would put us into this column, and we would multiply our glass by 0.67. So that would reduce our effective solar heat gain down by, a third. So the shading, the amount of shading you have does credit you. And what we thought we would do is work a problem like this one time by hand and then say, don't ever do this by hand. Use ComCheck. It's so much easier. Okay, so ComCheck will make your life easier. So, Brandon, here's the scenario. We've got several designers in this room that they've got looks like a retail building that's 50 feet by 70 feet, and the front is all glass, or almost all glass. It's a 10-foot wall, of which the top 9 feet is all glass, and there's a 6-foot overhang. Okay? So can we make, the architect is looking at 2 different options for glass. The first one has a low U factor and a high solar gain. The second one has a higher U factor and a lower solar gain. So the first thing that comes out is, does our U factor on option 1 pass code? Okay, not enough people said yes, so we're going to have to go back and find it. So 0.51. It doesn't say anything about the frame, but is 0.51 better or worse than 0.65? It's better, right? Lower is better. Is it better or worse than 0.60? It's better. So in other words, all of these options, we meet it, right? So are we good on U factor? Check. Okay, the next thing that comes out is solar heat gain coefficient of 0.52. Does that pass code? So the glass by itself is significantly higher than what we need, which is 0.25. Are you with me? Okay. So fortunately, though, we have an overhang. What are the dimensions on the overhang? 6 feet. And what's the distance? 9 feet. So what's our projection factor? Okay. So our projection factor is 0.67. So we come into this chart, and it says, all right, Brandon, the magic number multiplier is 0.56. So write 0.56 up there. And he's going to multiply 0.52 times 0.56, and the answer, are we going to make it, is the question.
Anybody got that?
What'd you get, Cam? 0.29. So do we pass prescriptive code? We do not. All right, let's try it with the next glass. This glass has a higher U factor, but would it pass code? I can't remember. I better go check. Yep. 0.56 is better than all these numbers. So we're good on U factor. And the solar heat gain in this case is 0.44. So we're going to multiply that times our lookup value from our table, which is 0.56. And in that case, do we make it? So we get a 0.24 something, and we make it. Okay? Who has questions about this? Yes?
All right, so I see that the multiplier they have is the north orientation and all other orientations, but shouldn't the south versus the east and the west, shouldn't they have their own?
That's a good question. So if you didn't hear it, the question is the overhang table here. So you get a certain set of credit for south, east, and west, and you don't get as much credit for north glass. That kind of makes sense, right? And that north glass doesn't get the sun doesn't shine as directly on a north window. But what I think we're trying to do is not make this table get more complicated. That's my theory, because you could have this for one for south and one for east and west and one for north, and you could have southeast, southwest, northeast, northwest. I think they were trying to sort of say, at some point, we're trying to not to make this code too complicated, and that's my theory of why it's like that. Now,
An overhang on the south side is
it doesn't have to.
completely different.
Yeah, I agree. I agree. Yeah.
It's riding that really fine line between, I've got a code official who needs to be able to determine whether or not this works, or, not trying to make the architect work too hard. So let's do that in a very simple prescriptive approach. But if you want to, Mike said, architects gone wild, you can sort of go build a simulation method and really get credit for all of that.
By the way, also, ASHRAE gives you this table, which gives you, a lot more credit for different size and bigger overhangs. This code book basically says overhangs come in 3 flavors: none, small, and big. Okay? So it's just a different way to approach this problem: none, small, and big. So you get no credit for an overhang, you get some credit, or there's a big size, but then beyond that, you don't get any more credit. So it's just a matter of not letting it get out of hand, is the only thing I can say, is not getting these tables to be 8 pages long, that kind of thing. What we thought we'd do, too, is remind you that the overhang can be, an open-air thing like this. It's a shading device is what it really is. And it can't be something that the owner can retract either. So it has to be a non-retractable, awning. But if it's attached to the building, it's permanent, you can take credit for it. This kind of goes into what you're saying, and what's your name? I'm sorry. Jake? James. And what this is a photograph of the Southface building that we built in the mid-'90s, and it shows southern glass, and it's exactly what you're saying. It's facing due south. We probably maybe got a 2-foot overhang here, and you can see that it's casting a shadow down a good 15 feet. Whereas and then the passive solar aspect of this, it says, I took that picture on the summer solstice. This is the winter solstice. The winter solstice, the sun is very low at high noon in the sky, and so the shadow line is above the tops of the windows, right? So we're getting full gain when we want it, and we're getting no gain when we don't want it. And really, at the end of the day, we're all about air conditioning in commercial buildings. So commercial buildings, the answer is put the biggest overhang you can stand. That's my answer. Put the biggest overhang you can stand. Big shading? Comment?
Let's say you went on the east or west side, you went with the more vertical.
Fins. Yeah. Yeah.
Is there a chart
There's not a chart. The prescriptive code does not recognize that. The only way to get credit is the simulation path, which would definitely credit you. And yes, you're right to be asking that question. That's a good thing to do. So air sealing is very explicitly spelled out in the commercial code. This is the list that they say. Basically, everywhere has to be, you have to seal here and all these places, and then at the bottom, anything else we forgot to mention. So lots of requirements for air sealing, including doors, which typically the manufacturer is going to hit that for you. But vestibules are a big one. Question? Oh, sorry. So any questions on vestibules? What we're going to do is watch a real short video about vestibules. So they have little videos and things on stuff, on aspects of the code. That was a kind of a fun one. You learn more than you ever knew about vestibules. Let's hit some of the key concepts, because this is a very big difference between the two codes. Okay, Brandon?
Well, based upon what she was just saying, if we built this building today, I'd say we probably have about 3,000 square feet.
Yeah, great.
Under the IECC 2009, you would have to have a vestibule on the front door, or a public entrance. What's different between that and ASHRAE 9.1 is that they say if it's 10,000 square feet and 4 stories above grade, then you're required to have a vestibule. And that's only if it goes into a space that's 3,000 square feet or bigger. They've got, again, the doors must be equipped with self-closing devices, interior and exterior doors must be at least 7 feet apart. But if it's less than 3,000 square feet, or if it has a revolving door, or if So again, you have to have a pretty large building, at least 10,000 square feet. And is it and or?
It's and.
It's and. So we keep going back and forth on this. And 4 stories above grade. That is the only time this will start kicking in. Plus, it has to be at least 3,000 square feet. So say you've got a multifamily, high-rise multifamily building. Maybe it's 30, 40,000 square feet, 7 stories. So you're saying, okay, we may have to take a look at that. If the lobby that goes into is greater than 3,000 square feet, you have to have a vestibule. If it's less than 3,000, then you do not have to have it.
And remember they said that, they also talked about a situation like in this building where the lobby out there is pretty small, but it opens right into the main space, right? So if we had solid doors there where those arched openings are located, then we wouldn't have, that lobby would be under 3,000. But since it opens right into this space and there is a fixed opening, then in this case we would need a vestibule. So I would summarize it by saying, if you love vestibules, this is your code. Because this code does not have that first bullet exception, whereas ASHRAE does. So if you think vestibules make sense some of the time, this is probably your code. If you love vestibules and you want to put them in almost all the time, this is your code. So that is a very big difference between the two, is that only ASHRAE, this only pertains to ASHRAE, this exception right here. Does everybody understand that? I think that's probably the big takeaway. So code officials, you're going to have to kind of ask yourself, is it opening into a space, less than 3,000 square feet? And if you go by Chapter 5, then I'm sorry, more than 3,000 square feet. If you go by Chapter 5, the answer is you need a vestibule, unless the exceptions apply. So I think that's a very big deal. The cost implications of adding a vestibule on a Walmart or something are pretty significant, but they usually would have to do it. The other big thing is other air leakage sites, like we said. Well, the short answer here is the ugliness occurs above the drop ceiling. So you push the ceiling tile aside, and this is what we want to see, and this is what we don't want to see. So that's, in essence, where the bad stuff comes from. And I got a picture. That's a kind of a cutaway, a section of a problem. But I think this picture really says it all. You probably have all seen moisture problems on drop ceiling tiles, right? And people think that's a roof leak, but it's not a roof leak. It's what caused that? Condensation. And here's a pathway. And if that space above the drop ceiling is a return plenum, what kind of pressure is it under? It's under a suction effect, right? A negative pressure. So you're sucking in humidity, and it's basically falling on something cold and condensing. So that's a very common problem in commercial buildings. Does that make sense? Without trying to beat that into your head, I think we got that down. This is the psychrometrics of that. So the last slide we want to say is you can actually do a test on commercial buildings if they're not too big. And that is an example of blower door testing commercial buildings that we do this in Earthcraft Light Commercial. And it can tell you some really useful things.
Yeah, again, in our climate zone, we sort of looked at moisture intrusion via diffusion and then via air leakage. Air leakage is a big issue because of very humid climate. This is by no means mandated by code, but I think this is something we're going to start seeing. Washington State has actually mandated it, and if anybody's doing work for port engineers, they're starting to do this.
Right.
Pretty large-scale blower door testing because they're actually seeing good benefits. So it's pretty cool.
One of the stories I like to tell, though, is there's a school on Claremont Avenue in Atlanta that was a fairly new school, and it was about a 12,000 square foot building, and they did it under the Earthcraft Light Commercial program. And the folks, to do this test, you turn off all the air handlers and everything, and you tape over all the mechanical openings, and then you depressurize. We usually depressurize the building because if there are dampers, depressurizing a building pulls them closed. And so, they had the blower door on for maybe 20 minutes, and it was a reasonably hot day. And so the system's been shut off, and, the temperature in the building, most of the building went up to, let's say, in the mid-high 70s. Well, then all of a sudden they walked into the library and they noticed that, wow, the temperature is much hotter in this space. It's in the mid-high 80s in this space. And what does that tell you? When you walk into a space like that and all of a sudden, it's a whole lot hotter than the rest of the building and you've been running a blower door, what does that tell you? What does that tell you about that room? It says there's some big leaks in that library. And so this library had what a lot of times you see is some kind of architectural feature, a suspended ceiling, a cloud. Anybody heard that term before? A suspended ceiling. And when you looked up above, sure enough, there was about a gap about this big that went all the way around that was effectively connecting it to, if you will, an attic. And so when they ran the blower door, they were able to fairly quickly diagnose this has a problem. And not to mention that the numbers were really high, but besides the numbers being high for the blower door, you can actually find the problem. You can use a thermal camera when you do this. So there's some neat things you can figure out. And that's one of those things that would have not been discovered probably without the test, right? It's a hole in the envelope. The air barrier is not continuous, but it's hidden. Nobody sees it. It would have shown up as lots and lots of moisture problems in the building, lots of comfort problems, high energy bills, but it would have eventually caused moisture problems, and maybe they would have found it down the road. You never know. So that's the argument for that. You look hungry and excited, so let's go eat some lunch.